today is to look at and hopefully complete 11.1. And as soon as we've done that, we'll do the beginnings of 11.2. So if you remember last time we talked about sequences, right? And what we're looking at right now are questions where you've been asked to find the limit of a sequence. And the typical techniques that you would use would be things like brute force. So an example of a situation where brute force might work well could be something like that guy. Because in brute force, you make the n infinite. So 1 over infinity squared plus 1 is the same thing as infinity, and 1 over infinity would get you 0. So that one converges to 0. But there are other situations where brute force doesn't work, and so we might use a technique like L'Hopital. And an example of L'Hopital would be this one here, where we've got the limit as n tends to infinity of 2 logs. There's the first log, and underneath it, there's a second log. Now, what L'Hopital says is that provided the original limit is indeterminate form, well, if you plug infinity into that top expression, the log of infinity is infinity, and that's true in the bottom as well. And infinity over infinity is one of the two situations that we would call indeterminate form. The other is 0 over 0. According to L'Hopital, what you can do then is that you can find the limit of the derivative of the top divided by the bottom. Right, now if you differentiate the natural log of 1 over 5n, you get 1 over 5n times 5, because basically it's a chain rule. And a chain rule, right, the inside function is 5n. So differentiate it, 1 over 5n times 5. If you take the bottom one here, it's 1 over 15n times 15. If I do a little bit of tidying up, essentially what we get is 1 over n over 1 over n, which actually is just 1. I mean, if you want to do an extra line to prove that, that's what the answer is. So brute force, you plug in infinity for the n, and you try and see if there's any kind of calculation. The types of things that brute force are going to work with are, are fractions, perhaps, where there's only one term that has an n in it, in which case you're going to get 0 and infinity. But if there's anything involving functions like this, you would need to do L'Hopital. But that is not the only kinds of questions or limits that you have to find limits. And those techniques work great, but they don't work every single time. So I've got a kind of selection here of other situations where we're still being asked to find the limit as n tends to infinity. But each one is a little bit different and requires its own strategy for solving.
What did you call the first one? The limit as n approaches infinity? You call that brute force?
Yeah, it's just a name. Brute force, you just plug in the number, you just batter it way through. Brute force. Just a name for the methods. Very often if you've got a name, it makes it easier to talk about it. Well, let's try this one. 16. Now, I'm going to look at this one, and I'm going to talk about what its limit is. And it's really not an algebraic method. It's not like L'Hopital, and it's not even really like plugging in infinity, at least not at the start. So here's my argument. Would you agree that cosine n can only take values between -1 and 1? And if you square it, technically you can only get answers between 0 and 1. So that top guy, the worst case scenario is 1. So I'm saying that the limit of this will behave something like the limit of this, right? It'll never be bigger than this. Now, if you plug infinity in here, 5 to the power of infinity is infinity, and 1 over infinity gets me 0. Now, there are other techniques for solving that same limit. One's called the sandwich theorem. And if you wanted to do it, which is much more formal way of what I just did, let's suppose we wanted to prove this a little bit more mathematically. I can tell you right now, oops, intense infinity, that this answer here is guaranteed to be less than 1 over 5 to the n. And on this side, I can guarantee that it's positive. Would you agree? Cos squared is positive, 5 over the n, it's definitely positive. This is positive, so it's going to be bigger than or equal to 0. Now, if you do this guy, you get 0. This fella is already 0. So the answer I'm looking for in the middle, the original, has to be between 0 and 0. Well, you don't have much choice if you're between 0 and 0. So the argument is that it has to equal 0. So there's one way of finding it. There's a slightly different approach, but the result is the same. Are we good? Any questions about that one?
So that only works because you have the cosine, right? And,
Well, if it was sine squared, it'd also be the same.
okay.
Because
So
sine
what-
can only be, minus 1 to 1. It's the squaring that makes that 0. Now, if that was just cosine then, right, just for argument's sake, if that was a cosine on its own,
So you just consider the lowest value that the cosine could make it, and then the highest value.
yeah.
On the right
So
side.
you,
Okay.
so you would do this. Now, if you make that go infinite, you get 1 over infinity, which is 0. If you make this go infinite, you get negative 0, which is 0. So it's still sandwiched between 0 and 0. So it still ends up being 0. So that's the worst case scenario, right? That's the lowest it could be. This is the biggest. So it's not that different, but cosine n could be negative. Isn't cosine squared guaranteed to be positive? That's why there's a slight tweak on this side. Now, if you replace cosine with sine, you get equivalent. It's virtually the same. Now, the next thing is something you might not know. It's, well, at least the name I know it by is called the relative growth rates of functions. Should really call them expressions. Some expressions get to infinity quicker than others. Now, what I mean by that is that if you evaluate the function at n equals 10, one of the answers could be billions and the other could be 2, right? All of them may go to infinity, will go to infinity, but some of them take different times, right? So here's a hierarchy. One of the slowest functions in the world to become infinite is the natural log of n. I'll give an example. If it was the base 10 of n, right, which is kind of similar, wouldn't the natural log, the log to base 10 of a billion only be 9? I mean, it's not that big, right? Even the American debt would only be about 12, right? So it's not really huge. But if you go far enough, won't that eventually become infinite? Now, the next one in the list. Square root of n. Actually, cube root and fourth root. The square root of n takes a long time to become infinite, but it does it quicker than that guy, right? The square root of 1,000,000 is 1,000. The log of 1,000,000 is 6, right? You see there's a difference. Now, the next one after that are powers like n cubed, n squared, n to the 4. That's much bigger. For any given value of n, let's say 1,000,000, that's the smallest, that's next biggest. 1,000,000 cubed is obviously bigger. So far, so good. Now, what do you think the next expression that's even better at getting to infinity than n cubed is?
E.
E to the n, 2 to the n, 10 to the n, anybody in that family will definitely get there faster, right? E to the power of 1,000,000 is much bigger than 1,000,000 cubed. You just have to trust me, because your calculator couldn't do it, right? Your calculator would kill over and die. So we've got that guy. Now, next. Have you seen the guy called factorial before? Because that's going to be my next question after this one. Do you remember what factorial is? So 7 factorial would mean 1 times 2 times 3 times 4 times 5 times 6 times 7, right? It would be multiply the first 7 numbers together. Well, can you imagine what 1,000,000 factorial would look like as a calculation, right? 1 times 2 times 3, all the way to 999,999 times 1,000,000, right? Huge. Doesn't take much for a factorial to get really big. And there's one last one. Well, who else is there? Who have I not included in this list that's even more massively big than n factorial would be for a fixed value of n? Any thoughts? What's missing? Nothing obvious.
Into the end.
Yeah. Can you imagine 1,000,000 to the power of 1,000,000 would beat all the other ones that came before? Now, why is this relative growth rate information important? If you get a limit and it involves 2 guys, 1 from each, right, 2 of them from this list. For instance, n cubed over e to the n, right? Now, you could do that by L'Hopital. You could also do it by the relative growth rates. And the argument goes something like this. If you have 2 guys from this list, one of them's going to be bigger, quicker than the other. And whichever one that happens to be, that's going to decide the answer. Now, in this particular case, would you agree e to the n is bigger than n cubed? So what happens is, if the biggest one is in the bottom, you are going to get basically a number, right, over something that's huge. So the answer is always 0. So if the big one is in the bottom, the answer is 0. If the big one is on top, the numerator, like it is here, then you get infinity. So when you use the relative growth rate, when you're comparing a fraction, one function over the other, all you need to do is to look at which one of them is going to be the biggest, right? Which one's going to win? If the one in the top is bigger, the answer will eventually be infinite. If the one in the bottom is bigger, the answer will eventually be 0. Right? So you can imagine 1 trillion is big, but like 1 trillion cubed is bigger, right? It's going to beat you. Are we cool with that? So,
Cool.
if I gave you a question such as, because I know I've got one floating around here somewhere, such as 7 to the n minus 1 factorial over 7 to the n plus 1 factorial. Which one of these two is the biggest? Top guy or the bottom guy?
I'll say the bottom.
Right, because isn't that a larger factorial than that one? Agreed? And if the bottom one is bigger, the answer is 0. Now, if I turned that upside down, wouldn't the answer be infinite? Okay, what about this one? This isn't one I've got in the homework, but just random. If I went and said to you n factorial over n to the n, would the answer be 0 or would the answer be infinity?
0.
Correct, because this is the big guy in the bottom. If I went and said to you the limit is n tends to infinity of n factorial over e to the n, what would you get this time?
n factorial is bigger than e to the n, so you're gonna get infinity.
Right. So to solve those questions, there's really not any algebra. Isn't it just I know from the list of relative growth rates which one is going to be the biggest and therefore the answer? For instance, if I went and said to you, the limit is n tends to infinity of 9 to the n over 7 to the n, which one would win?
Then 9.
Right. And wouldn't that make the answer infinite then? Big guy on top. Okay, well, I've actually just noticed the question. This is 22. 22 has 9 n factorials over 2 to the n. Which one's the biggest? Top or bottom? Which one's the biggest?
Top.
So the answer is infinite. Agreed. You cannot do L'Hopital in that. I don't even think there is a derivative of n factorial. At least I've not seen one. Would you agree? You can't really do brute force, because if you do that, don't you just get infinity over infinity, which isn't any use to you, right? So you need some other way of dealing with situations like this one, where the typical methods that we've learned really don't apply. Right, got a guy here called 19, different tack, different question. Right, see this guy here? It's 2 log subtracted. That's really not in a form that's going to do me any good. But if you subtract 2 logs, can't you combine them into a single log, where the first one goes there, divided by the second one goes there? Are you okay with that? A log, take away a log, becomes a log of a division. Now, here's a little trick you're allowed to do. If you're doing the limit of a function like a log or a square root or whatever it might be, you are allowed to switch places.
Yeah, I remember that.
Now, this one here, you can actually do by L'Hopital. You can do it other ways as well, but are you comfortable? The answer is 6. Do you recognize that this would be 6? And so the answer isn't 6. The answer is the log of 6. Remember, the log's still there. I've just changed the order that I apply it. Not that I've changed that it's, made it so it's not there anymore. How are we doing?
So why is the answer 6?
Well, this guy is 6, right? And remember, it's a natural log of the answer, the natural log of 6. See, it's a natural log of a fraction.
Right.
We've moved the limit inside. The limit inside says this is 6. The log is still there, so it's a log of the answer you got, the log of 6.
Okay.
Right. Same type of question. Imagine someone gave you this. Square root of 6n squared plus 6 over n squared plus 6. Suppose they asked you to do that. That'd be horrible to do with L'Hopital or any other rule. But why don't you change the order by switching the places of the square root in the limit process? So can't I find the limit of this fraction first and then take its square root? Well, we know that the limit is 6, so the answer in this case would be square root of 6. And couldn't I do the sign of that fraction, e to the power of that fraction, the cube root of that fraction? Pretty much any operation like that, you can switch places, do the limit first, and then do the square root, the log, whatever it was you did last, do it to the answer to the limit. And that gets you around some situations that would be too difficult otherwise. Well, here's one that hasn't even got a formula. You either have a limit, in which case it's 0 or 1 or 42, right? It's a number. And when that happens, we say that it converges to 0, 42, a half. or it diverges. Diverges mostly means that the answer is infinite, but couldn't diverge just mean it has no answer, right? There's no limit, no normal single value. Does this sequence have a limit as n tends to infinity?
No.
No. Now, I can't prove it algebraically. I wouldn't want to even try, create a formula for it and try and do L'Hopital. It's just not, you don't do it that way, right? There are some things you just have to do by logic. Would you agree that no matter how far this sequence travels, no matter how many zeros you do, aren't you eventually going to write a 6 again?
Yeah.
You can't jump between 0 and 6 and have a limit, right? Even if there's a lot more zeros than 6s, the limits don't care about that, right? The limit cares, does it head to one number and never deviates from that? No, this one heads to 0 and then it jumps up to 6 again. Then it heads to 0, but then it jumps up to 6, and it will do that jump up to 6 forever, which makes this one divergent. So the word divergent is your catch-all phrase for it doesn't have a single limit. And there are lots of different ways that can happen. Here is a trick question for you. And I'm telling you right off the bat that it's a trick question. The limit as n tends to infinity of the tangent to 4n pi over 3 plus 16n, right? Put little brackets around that for emphasis. Now you can switch places. So here's the tangent of the limit as n tends to infinity of 4n pi over 3 plus 16n. Are you with me, Sol? Right. So I'm switching the tan and the limit. I'm doing it. I'm changing the order I do things. I'm not changing anything else. So I'm going to find the limit of this first and then get the tan. Okay. What is the limit of this ugly, ugly fraction as n tends to infinity?
Infinity?
Well, if you put in infinity for n, you get infinity over infinity. So that's not going to work.
see,
I
I
would
could
say 0
Yeah.
because the bottom's gonna race up quicker.
Well, yeah, but not that quick compared to this fella. Do you see that's a 4n and that's a 16n?
Yeah.
Yeah, so if that was 16n squared or just n squared, I'd agree with you. Or if that was n cubed and this was n, I would agree with you. But since they're equal, they're kind of going in the same road, roughly at the same speed, right? The multiple of 4 and 16 makes a little bit of difference, but not enough to make it 0 or infinity.
So if you have infinity over infinity, you can do L'Hopital's, right?
Correct. Okay, let's do L'Hopital. If you differentiate that guy, you get 4 pi. And if you differentiate this guy, you get 16. Ah, wait a minute. Isn't the answer a quarter pi?
Tangent of quarter pi is
It's 1. If you check your unit circle.
1.
Now I'm going to zoom over to the last few questions in the homework now and just kind of talk you through. The one I just did a few months ago is 25. First, are you looking at 26? Am I in the right place, are you guys?
Yeah.
Okay. In this question here, that guy there is L'Hopital. Can you see why it's a L'Hopital? You could divide, you can differentiate and you're good to go. Maybe I'll make it a little bit bigger. I'm not sure what kind of size screen you're working on. There, does that make it a little bit clearer? Right. That's L'Hopital, and the answer will work really well. I believe it's a 6, but you can check it.
So before we even make the decision to do L'Hopital, can we just plug infinity into the equation and see if you get infinity over infinity?
You should, because you shouldn't use L'Hopital if you don't.
Right, but I mean, that's the check, right? That's
Yeah.
the whole, okay.
Right. If you plug in infinity and you get infinity over 4, then the answer's infinity. And if you get 15 over infinity, the answer is 0. But if you get infinity over infinity, which is most likely thing, but sometimes you get 0 over 0 because that also counts, then you're on L'Hopital as a candidate. It's not necessarily the only way to do it, right? We've shown you today some other ways that might be more efficient if the equations or the expressions, I should say, are things like n factorial, right? You don't want to do a L'Hopital if one of the terms is n factorial, right? Because you can't differentiate it for starters. Now, if you were going to do this one, wouldn't you switch the order?
Yeah, I
Wouldn't
would
you
take the
think-
square root out.
Take the square root out, get the answer, and then once you've found out what it is, take the square root of what it is. I think that comes out as a 5th. Now, what do you do if you don't have a formula? Here's a sequence where all they've done is give you the first few terms, and it asks you to find a formula for it. And then maybe not this time, but sometimes they then ask you to create, to find out whether it has a limit as n tends to infinity. So we need to create a formula for this guy. Let me show you my thought process behind this one.
N plus 2, 1 over n plus 2.
Well, we have 1, we have a third, we have 1/5, we have 1/7, right, and off it goes. First thing I'm noticing, even 1 can be thought of as 1 over 1, right? So I'm looking at this formula, I'm saying 1 over, because everybody has a 1. And then I'm going to focus on, well, the first answer gives me 1, the second answer gives me 3, the third answer gives me 4, and the fourth answer gives me that guy. And I'm trying to find out what the nth answer is, right? Well, I know it's 1 over. We've got that already. Do you recognize an arithmetic sequence here? 1, 3, 5, 7. Right, it's on the bottom, but it's still, that list is still arithmetic. So 1, 3, 5, 7. Arithmetic because you're adding 2 all the time, right, to get the next number. Now, A is equal to 1, and there's a guy called the common difference, which in this case is 2. And if you're an arithmetic sequence, your formula would be A plus n minus 1 D. And I'm telling you that because that's what it is. The formula for all arithmetic sequences is A, where A represents the first number, plus n minus 1 times D, where D is what's called the common difference, what you're adding each time. So in this case, it's 1 plus n minus 1 times 2. I'll stick it there. That's 1, 2n take away 2. I get 2n take away 1. And since it's on the bottom, I have that. So there is the formula for that fraction. 1 over the odd numbers, 1 over 2n minus 1. I can check it, right? Shouldn't the fourth answer be a 7, right? 1, 2, 3. Fourth answer should be a 7. Let's see. A4 is 1 over 2 times 4 take away 1. Yeah, it works. Yep, there's our formula. Anytime you see an arithmetic sequence, even if it's on the bottom of a fraction, use this formula to get what it's equal to. For argument's sake, just suppose, just for argument's sake, that this is what you got. 1, 2, 3, 4, right? So 1 over 1, 2 over 3, 3 over 4, 4 over 7. Right, imagine that was happening. I'm now going to look at the top. The first answer is 1. The second answer is 2. The third answer on the top is 3. The fourth answer is 4. Wouldn't there be n on the top? And that's how I would create that. So sequences can have, do very often have formulas. Trying to find out what they are is a kind of an art where you try and look for patterns. In this case, the pattern was arithmetic sequence. This is another one, but this is a different kind of sequence. Do you recognize this as a geometric sequence? Right. Geometric, you start with the number and then you keep multiplying. If you start with 1 and you wanted to get -1/4, you would have to multiply by -1/4. If you take this guy and you multiply him by -1/4, you get 1/16. If you do it again and you multiply this guy by -1/4, you get this fella. And if you do it one more time, you get -1/4. If ever you have a sequence where to get one number onto the next, you just multiply by the same amount as we have here, the same amount is called -1/4. We have a geometric series. Geometric sequence, I should say. And it has a formula. And its formula is A times R to the power of n-1. A is the first number. So in this case, it's 1. And R is the common ratio. In this case, 1/4. So here is going to be 1 times -1/4 to the power of n-1. Well, if you multiply something by 1, it doesn't actually matter. You don't need to write the 1 down. Here is the formula for that sequence. So if you ever see a sequence where you start with one number and you multiply by 5 times 5 times 5, or times 1/4, or times -1/4, its formula is A, the first number, times the common ratio to the power of n-1. In this case, you tidy it up afterwards. And that's us finished with sequences. I've pretty much covered everything. Is there any questions before we move on to series?
I missed the part we talked about the little exclamation points.
So factorial they're called, right? So, and they look like that, right? The little exclamations. What do you want to know what they are and how they work? Natalie? I'm not sure what you want me to do about these things.
Did we talk about that class or was that earlier? Minutes in the beginning.
I did talk about it a little bit earlier. Here's an
I can
example
rewatch.
of one.
I can rewatch the video later if it'll take
Okay.
too much time.
Yeah, I can give you a quick. It's always good to, when someone's new like this. Right, so first, if someone says to you, what number, what's the value of 3 factorial? It means 1 times 2 times 3, so it would be 6. Now, if someone said to you, what is n factorial? You would say it's 1 times 2 times 3 times, well, eventually, until whatever n is, that would be its definition. And so n factorial basically means 1, 2, 3, up to whatever number n is, which means factorials must have a positive number here. You can't have 3.5 factorial, right? It has no meaning, at least in the context we have here, right? So it's 7 factorial of 10. Eric?
I think number 22 would be a great one to go over.
Okay, let's do that. I'll scan back and find it. Okay. In question 22, we're being asked to find the limit as n tends to infinity of 9 to the power of n. No, it isn't. 9. Let's do that again. 9 times n factorial, put a little bracket to emphasize it, over 2 to the n. Now, both of those are going to be infinity, right? So if you plug infinity in here, you get infinity. And infinity over infinity is bad news because you can't really tell what the answer is. We call that situation indeterminate form. So what we do instead for that type of question when you've got two expressions, which I'm now trying to find my list, which I wrote down somewhere, which is the relative growth rate, which is here. You use this list here to help you out. What this list basically gives is from expressions who get to infinity really slowly and finishes with expressions that get to infinity really quickly. This is the fastest, at least the one you're likely to see is this one. Now, n factorial is there. 2 to the n is in this family. I know it says e to the n, but 10 to the n, 5 to the n, 2 to the n, they all belong there too, right? Anything exponential belongs here. So the big guy is on the top and the small guy is on the bottom. And these are relative growth rates. Wherever the biggest one is decides the answer. So if it's on the top, the answer is going to be infinity because that's going to get big so quickly, it'll overwhelm the value of the bottom. So the denominator might be huge, but if the numerator is like huge, 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 it overwhelms it. And infinity is the result of that calculation. Okay.
Okay, yeah, that's way different than you explained it because I watched the video on that and it kept like listing out the series like A1, A2 and things like that.
Yeah. Are we which video? I'm just curious. Which video are we talking about?
Oh, because I started the homework and it was the
Huh.
where you press that watch button.
Okay. Yeah, well, people do it differently. So I don't know if they do it better very often than they do, but sometimes they don't. And I just noticed one that I missed, and it's a one-off question, but I'm going to have to show you it. Question 18 is magic. And what do I mean by that? I mean, I'm going to tell you how to get the answer, but it might not be particularly obvious what you get. Whenever you get an expression that looks like this, so in general, this is the expression I'm talking about. 1 plus a over n raised to the power of bn. So a and b are numbers. In this case, it's 5 and 1. These guys always have a limit of e to the power. And it's a times b. So that's the magic. The limit as n tends to infinity of 1 plus some number over n, right, raised to the power of bn is e to the ab. So this one is 1 plus 5n raised to the power of 1n. So that guy would be 5. Are we cool? Right. Let's do the simplest version of that one. According to my formula here, what should 1 plus 1 over n raised to the power of n be equal to? One plus a over n raised to the power of b over n. What would 1 plus 1 over n raised to the power of 1n be?
1.
Yeah. So e to the 1. Right, is e to the power of 1, e to the power of 5, e to the power of whatever a times b is. Now I'm going to, that's magic, because I'm telling you, and you just have to trust me. I'm going to be putting on Desmos that particular sequence to try and convince you that it's true. So I'm going to go here and put in brackets 1 plus 1 over n raised to the power of n. Okay. And I said that the answer is E, right? About 2.7. Okay, let's just click on this a little bit more. Right. Here is the graph of the first 300 terms. Does that guy look like it's heading towards E? Have I convinced you that it's right? Now, if I change this guy here to a 2, then wouldn't the limit be E squared? Let's check it out. Can you see it leveling off to E squared now? Will we take that as a proof-ish? It's not a real proof, but would you agree it's valid? It works, right? I tell you what the limit is, and it ended up being what I said it was going to be. And there's the graphical proof of it. If you look at it, it levels off, in this case, it now levels off at E squared. And technically you could do anything you like. Oh, what would this one be? What would 1 minus 1 over n raised to the power of n be equal to? E to the power of what number?
Minus 1?
Yes. And I'm going to have to change my scale so you can see it. Yeah, you see it working? It's leveling off at e to the minus 1. Okay, that's me now finished sequences. Any other topic, questions, whatever, before we move on? We good? Then let's do 11.2, at least start it today. Introduction to series. Now, imagine I have a sequence. Any sequence will do. So let's suppose my sequence is 1 over 4, 1 over 9, 1 over 16, 1 over 25, forever, right? The formula for this particular sequence is 1 over n squared, agreed? You can check it. So what is a series? A series is the sum of all the terms in a sequence. So if we have this sequence, its series would be this fella. 1 plus a quarter plus 1/9 plus 1/16 forever. So a series is what you get when you add up all the terms in a sequence. So if you added them all together, right, all the way to infinity, what would you get? And no, the answer is not infinity. Some series add up to a number, add up to 4, 42, a half, minus 10. Many of them don't, And when they add up to a number, so when a series has a finite answer, just a fancy way of saying the number, we say it converges. And very often, but not always, we'll say it converges to 2, right? It converges to 42. And if a series does not have a finite answer, we just say it diverges. It's kind of similar language, although it's a different idea. Don't you say that a sequence converges to 4 or it diverges? I know that we say diverges when the answer is infinite, but can't you diverge because you jump between 0 and 6 all the time? For instance, in a sequence, wouldn't that diverge? Because doesn't that have no answer? Right, won't the sign of n just bounce between randomly numbers in the 1 to -1 range, right? There's no particular final destination as n becomes infinite, right? On the other hand, wouldn't that also diverge? But now it's diverging because the answer is infinitely large. But the whole lot of them are included in the term diverges. So when you say something diverges, you don't need to be too specific about the reasoning for it. You just say that it does. Now, on the other hand, when something converges, you would probably expect that it converges to a single value, which it does and has to. But strangely enough, you don't always need to find out what that number is. You only need to prove that that number exists, right? That it will converge to something, even if you don't go to the trouble of finding out what that, magic number that it converges to. So we tend to introduce a particular notation for doing series. Because in series you're adding up a whole load of things, it's very cumbersome to write it down like this. So you would typically write a series down like this. Have any of you seen sigma notation before? Do you recognize it? That is essentially saying this in a much nicer way, isn't it? It's saying, look, plug in n equals 1, then plug in 2, then plug in 3. So if you plug in 1, you get 1 over 1 squared, then you add 1 over 2 squared, then you add 1 over 3 squared for eternity. And that's the 1, the quarter, and the 9th, etc. Are we good? Right. Now, the choice of n is quite arbitrary, right? It could be anything. It's totally okay, for instance, to do that with a sequence. Would you agree that that series means exactly the same thing as that? It just uses k instead of n, right? So series are typically written using sigma notation. Very often you'll see n's, but you could see k's or any other letter of the alphabet they choose, but k is very common. So far, so good. So now our quest becomes trying to find, well, let me leave this for a minute. And let's find our guy. Come on, where are you hiding? There we go. I'm just busily quickly trying to load up our next section. So our quest becomes, does this guy converge or not, right? And there are going to be, oh God, I think it's 11 different tests that we need to find out if a series converges or not. So there was one section on sequences, and there's like 11 sections on series, right? So it's very heavily weighted on series. So here is our first test. Test number 1 of the many that have still to come. This test is called the divergence test. And you've got to be looking at what I'm about to write as if you're a lawyer, looking for loopholes, right? So here goes. A series, sigma n equals 1 to infinity an, right? So would you agree that's pretty much every series in the world could be written like that? Is divergent if the limit as n tends to infinity of an, right? So if the limit of the individual terms is equal to L, where L is not equal to 0. So if that, not the sigma, but just each individual term, if that limit is a number, we'll call that number L, and L is not 0, then the series diverges. If, however, L is equal to 0, the test is inconclusive. That means we do not know if this particular series converges or not, right? If this test had two sides to it, where A, if this happens, it diverges, and if this happens, it converges, do you know we wouldn't need 11 or 13 tests? Wouldn't we just need one, this test? That is a big problem, because unfortunately, many series, the limit is 0. And some of them converge and some of them don't, right? And we can't tell. If you're lucky, you'll get this happening. Okay, so here is a sequence. Yes, it is a sequence. Now, it has two parts to it. This is essentially question 1. The first part says, find the limit as n tends to infinity of en. Right. If you look at this fraction, can you tell what the limit is going to be? If you want to use L'Hopital, go ahead. If you want to divide the top and bottom by n, that also works. But does anybody, can you look at that and tell me what the limit is going to be? It would save me time. And I wouldn't need to do it. Right. 5/10, 1/2. Agreed? Now, that's part A. Part B then says, determine whether the series of this guy is convergent or divergent. Well, we just found A, the limit is 1/2. According to the divergence test, if the limit is 1/2, can we say that the series diverges, or do we have to say it's inconclusive? That's the only two choices we've got. Does this series diverge, or is it inconclusive, given that the limit of the individual term is 1/2?
Diverges.
Yeah. Isn't the limit L 1/2? It's not 0, so it diverges. So this test only tells you when some series diverge. It doesn't tell you about the rest, right? But if you're lucky enough to get a limit that's not zero, you know that that series diverges. If you don't get if you do get a limit of zero, right, then you don't know anything, right? It's inconclusive. So that's test one. It's called the divergence test. Okay. Suppose I give you this as my sequence. Well, let's cut to the chase. Let's put it all together. That's better. Okay. I want to know, does this series converge or does this series diverge? The way I would do it is I'd find the limit as n tends to infinity of this guy. Let's suppose I decide to use L'Hopital. Okay, the limit is 1. So the limit of the individual terms is 1. Convergent or divergent? What does that tell? Well, sorry, divergent or inconclusive? That's the only two real choices you have. Divergent or inconclusive?
It's not zero.
Okay, so what does that mean? You're right, it's not zero.
So according to your rule, it means it's divergent.
That's it. Yeah. You just put a little sentence, well, if you were doing it in paper, by the divergence test, the series is divergent. One more of this fella. We'll see others, but right now, one more of them. Now, if I try and find the limit as n tends to infinity of 1 over n cubed, I can just do brute force on that. And I get the answer 0. What's my conclusion this time? Divergent or the test is inconclusive?
Inconclusive.
Okay. You know, we don't like inconclusive because basically we're no better off than we were when we started, right? We don't know what's going on. It might converge, it might not. One of the other tests that we'll do will be able to show you what that one does. So here's test 2 of the many tests that we're going to learn. And this is called the geometric series test, or for short, GST. And by the way, divergence test for short, we'll just say DT now, right? So the geometric series test says the following. This is important. If you have a geometric series and the common ratio R, right, has the following properties, right? If the absolute value of it is less than 1, the series converges. If the absolute value of R is greater than or equal to 1, the series diverges. So that's a much better test, isn't it? Because now you can only be one or the other, right? There's no sitting on the fence, you know, inconclusive, right? But this test only works for a geometric series. Right? Secondly, on top of that, which you don't often get in tests, but this one you do. If the series converges, then its sum, which we'll call S, is equal to A over 1 take away R. So we can even tell you what the geometric series adds up to. We're not just going to say it converges or it diverges, right? We're going to say it converges or diverges, and when it does converge, we'll tell you what it adds up to. So let's show you a geometric series. There's a very straightforward one. That one. Its formula is, you can just trust me right now, is that guy. And so as a series, it would look like that. Now, to be able to do this test, all we need to know or find is what's called the common ratio R. Now, if it was written like this guy on the top here, where you saw each of the individual terms, couldn't you just pick any two and divide them and say, oh, you're going to multiply by a half? Agreed? So the common ratio here is multiply by half, multiply by half, multiply by half. So far, so good. Now, the absolute value of that is still a half. That really only matters when the common ratio is negative, you know, like you multiply by negative a half times negative a half and so on. Now, since this is less than 1, conclusion, the series converges. So the series, if you wanted to write it down, you know, as a calculation, would be what you get when you add all these guys up. And we've just said that that actually converges to a number, right? It's not infinitely large. And not only do I know it converges, I can even tell you what its sum is. It's A over 1 take away R. It's 1 over 1 take away a common ratio, which is a half, and that gets you 2. Does that seem reasonable when you see the pieces that it made from, that it would eventually get closer and closer to 2? Are we good? Any questions? Okay, then let's show you how WebAssign kind of makes your life a little bit more interesting. This is question 2. So we have 5 take away 6, add 36 fifths, take away 216 25s, and it adds and subtracts that. Now, the question tells you it's a geometric series, because sometimes you can look at something and not know that it's geometric. A is the first number in whatever the sequence happens to be. Now I need to figure out a way of calculating R. Now the common ratio is basically, what do you multiply this guy by to get that one? What do you multiply this guy by to get that one, right? And it's going to be the same number each time. The easiest way to do that, and I'll just give these little labels. A1 is the first answer, A2 is the second. The simplest way to do that is just to divide the second answer by the first. Would you agree that tells you what the ratio is going to be, right? So take that and divide it by that. So what do I get? I get negative 6 fifths. So if you multiply this by negative 6 fifths, you'll get that guy. If you multiply this by negative 6 fifths, you'll get this one and so on. So I know it works. Now, the absolute value of it is 6 fifths. And 6 fifths is bigger than 1. And well, what's the conclusion if the common ratio is larger than or even equal to 1? What's the conclusion that you come to?
diverges.
So by the geometric series test, the series diverges. And if a series, as this one does, diverges, that's the end of the question, right? Oh, what does it add up to? It really doesn't matter what it adds up to, if it adds up to anything, right? It just means it has no fixed answer, and that's all we care about. We don't need to go any further. Here's an example of question 4. We have 10, then it's take away 2, then it's going to be add 0.4, then it's take away 0.08. A is equal to 10, and our common ratio, you can hear barking, our dogs don't like people coming to the door. A2 divided by A1. So -2 divided by 10 equals -0.2. Hold on a moment. Let's see if I can do something about this. There we go. Are you comfortable about how you find the common ratio when you're given the series written down like this? This guy divided by that guy is my common ratio. Now my argument goes something like this. The absolute value of that guy is 0.2, and that is definitely less than 1, agreed? And so it converges. So by the geometric series test, the series converges. And when it does converge, they normally want you to find its sum. And I call that S. And it's A, 1 take away R. It's, in this case, 10, 1 take away 0.2. And if you take that calculation, I'm doing it right now, 10 divided by 0.8, the answer I get is its sum is 12.5. So believe it or not, I can tell you that if you continued this series to the end of the universe, it would converge to the number positive 12.5.
And so would that be the 1 minus the absolute value of R on the bottom?
No, oh, thank you for noticing that. I made a mistake. It's 1 take away the untouched R. So
Okay.
that answer has to be changed then. So it's 10 divided by 1.2, and that's 8.33. Actually, doesn't 8.33 make more sense when you look at the first 4 terms? No, it's the untouched value in the sum. It's the absolute value in the test, but the untouched value in the sum. How are we doing with the geometric, right? Find out who R is, absolute value it. If it's less than 1, it converges. If it's bigger than or equal to 1, it diverges. And off you go from there. Not all geometric series are written out in full format. Many of them get written in sigma notation. Here is a geometric series written down for you. They tell you in the homework it is a geometric series, but you should be able to, after a while, get used to it. They have this kind of format, right? A number times some fraction or decimal to the power of n, n plus 1, n minus 1, as it is here. Now, here's a nice thing. You can actually get the common ratio out of this formula here without doing any real work. It's staring us in the face, in fact. What is the common ratio for this series? You don't need to do any working. It's staring us in the face. What is the common ratio? You all think it's a trick question. About to tell you the answer.
5.
Oh, you went the wrong way.
Oh no.
0.6. So if this guy had been, well, let's put it down here. If this guy had been 5, 0.6, say to the n plus 1, or 5, 0.6 to the n, or any other version thereof, the common ratio would still be 0.6. The common ratio is tied in here, and the reason it's tied in here is, isn't this n just telling you how many times you multiply by 0.6 to get to the nth term? So that's what the common ratio is basically. What do you multiply by to get the next term or the next term after that and so on? Now, back to this guy. The absolute value of it is 0.6, which is clearly less than 1. So would you agree it converges by the geometric series test? Agreed? Common ratio 0.6, converge. But they want to know its sum. Well, that's A over 1 take away R. Well, I know who R is. The untouched value for R is 0.6. And that shouldn't be there. And that's going to be eventually 0.4, right? How do you find A? Well, it's easy when it's that, because it's the first number, right? It's not so easy to find out A when it's written down like this. So what you need to do is you need to take n equals 1 and plug it in to this expression. So when n equals 1, I get 5 times 0.6 to the power of 0. That's 5 times 1, that's 5. So in this case, A is 5. And so you have 5 on the top. And 5 over 0.4 should come out pretty nice, I think, 12.5. The common ratio is always going to be easy. It doesn't care if that's n plus 1, n plus 2, n minus 1. It doesn't even care if this is n equals 2 or 3 or n equals 0 or n equals 1. The common ratio is this guy here. You can do all sorts of things to it and it won't change the R value. The A value, however, is more susceptible to what's going on here. So in this case, the common ratio is still 0.6 and it converges. The A value is much trickier. If you plug n equals 1 into here, you're going to get 5 times nothing 0.6. 1 plus 1 is 2 squared. So you're going to get 5 times 0.6 squared. You're going to get A is 1.8. You see it's different from it was here. Now, in this case here, do you see the only difference is I made n equals 1 to infinity, but the only real difference is that. In this case, A is what you get when you plug in the first term. N equals 1 is the first term. 5 times 0.6 to the 1. In this case, you get 3. But I have seen series that do this. Let's suppose it's that one. The first term is whatever this number that I'm pointing at is. Most of the time it's 1. Sometimes it's 0. Less often it's 2. The first number is 2, right? So nothing 0.6 squared. And that ends up being 1.8. So finding the A is going to be the troublesome part, right? Getting R is easy. I don't care what you do with it. R is 0.6, right? You don't have an issue with that. Are we good? Now, this one is a version from the homework, 7. Right now, it doesn't look like we can find A or R easily. but I should be able to get A. Let's do that one. A is what you get when you plug in 1. 3 over pi to the power of 1. Well, the answer to A is it's that guy. Now, how do you get R? There are 2 ways to find R in a question like this. The first one is algebra, and the second one is basically just calculation. So here's algebra. This thing can be thought of as 3 times 1 over pi to the n. Does that seem reasonable? And then this can be thought of as 3 times 1 over pi to the n. 1 to the power of n and pi to the power of n is the same thing as that guy. So in this version, R is 1 over pi. Here's the second way to do it. A1 is what you get when you plug in 1. We've already done that. It's 3 over pi. It's the same guy as A. A2, the next one would be plug n equals 2 in here. So you can see what the third term, fourth term, and 10th term would be if I did them. Now, to get the common ratio, don't you just take the second term and divide it by the first? The second term is what you got when you plug 2 in. That's this guy. Divided by the first term. So top fraction times reciprocal of the other one. Do a bit of cancelling. There you go. Still 1 over pi. So you can either rearrange it algebraically so that it looks more like the way it needs to figure out who R is, or you can just figure out what the first 2 terms are and divide them. Right, plug n equals 1, n equals 2 in this case. Oh, now back to the second part of this. We've found the common ratio is that guy, and the absolute of that guy is still him, and he's less than 1, so we know it converges. Agree? 1 over 3.1 is definitely less than 1. So this converges by the geometric series test. So what does it add up to? Because that's what they would typically expect you to do next. Well, we know who A is, right? It's 3 over pi. And we know what R is. It's 1 over pi. So that's what it adds up to. Eric, you looking at this ugly fraction? Can you see it? Do you think that's good, or do you think we should make it pretty?
I think you could make it prettier. You can make the 1 and 2. You can make the 1 have its denominator be pi over pi.
Okay, so let's do that. Multiply by a special version of 1 pi over pi. The top 2 gets you 3. Pi times this guy. Take away pi times that guy. Would you agree that's a much prettier answer? And so style points is what we'd call. You like that guy?
Yep, much better.
Yeah, much better. This question, I think, was designed to try and catch us. Okay, here's the series. If I turn that into a formula, can you trust me it's that guy? Can you see the 3, 6, 9, 12 is an arithmetic? So this is not a geometric. They never did say it was. Right? But the problem we have got with this guy is, what does it converge or diverge, right? Which is it? Now, I can't use a geometric series test, but I am going to use something I'm now about to tell you. this series here, right, 1 over n, right, which basically is 1 plus a half plus a third plus a quarter forever, is called the harmonic series. In fact, isn't 1 comma a half comma third comma a quarter, isn't that called a harmonic sequence, right? So a harmonic series is just what you get when you add up a harmonic sequence. And I'm telling you this, you just have to accept it's true until we do the integral test, that it diverges. Okay. So we assume that this is known truth. Let's return back to this question here. 1/3, 1/6, 1/9, 1/12. I am going to pull out a common factor of 1/3. If I wanted to do it as a series, I could pull out 1/3 from my sigma and do that, which is the equivalent of what I'm doing here. Here's my argument for why this one also diverges. Would you agree that that's a harmonic series? And doesn't that add up to infinity, right? It diverges. Is 1/3 of infinity any less infinite than infinity? No. So that diverges too. So here's a truism. If you have a divergent series and you multiply all the terms by 5, or you multiply them by 1/5, it doesn't matter which, the new series is equally divergent. And the argument goes, if something adds up to infinity, do you think having all the terms is going to make it add up to less? Well, it's going to make it add up to half infinity, but isn't half infinity still infinite? So, yeah, no damage. It's still divergent. Are we okay with the logic that I tried to use to convince you that this diverges? Assume that this is a truism, right? We just told it's true. You can use this to decide if that or that, depending on which way you want to tackle it, is also divergent. And just to show you, you don't always need n. Here's one with k. Okay, here is the series. Prove to me, because it does, that this is divergent. Now remember, there's only 2 tests, divergence test or geometric series test. And I wouldn't even call this a test, but if you're a version of the harmonic series, that's a special case. So let's forget about the special harmonic, because that's definitely not a harmonic. So I've told you it diverges. How do you know I'm telling you the correct answer? Okay.
Well, it's based on what you told us so far, I would imagine it's geometric.
Oh, it's not a geometric. Said
No.
that.
Okay.
But look over here.
Okay.
What do you know about the limit as k tends to infinity of the individual terms of this series? What does that limit equal? Just by looking at it, can you tell that it's going to equal something? Now you can do L'Hopital twice if you don't want to, but you should be able to look at it quickly. What would
Okay.
you get?
1/2.
And what does that tell us? Well, if the limit ain't 0, it diverges. So it's divergence test.
Okay.
So it's divergent by the divergence test. So there's only two guys in the world right now. There's geometric and there's divergence tests, right? Geometric will look like this. Right, if you see something that looks like that, it's geometric. If it doesn't look like that, then you're probably going to be using the divergence test. So let's zoom over to some homework questions and see what we got here.
Also, how we're gonna know which test to use, or is that all by experience?
It's all by experience. The good news is that this section only has 2 tests in it, and almost all the tests are in one section, right? So you'll do a whole load of questions that are all the integral test, and a whole load, or p-test as well, a whole load that are the ratio tests, right? Each test, you get to see them. And then you get used to, by experience, what's going on. Right, look at this guy here. Do you recognize that that's going to be a divergence test? Just to look at it, right? Can you see it looks nothing like a geometric series? Now you might be seeing that guy, but I don't see that guy. I see 3 plus that guy. That makes a difference to me. Right, can you see this guy? Would you agree he's definitely a divergence test? There's no way in the world that's a geometric, right? And you're only interested in finding the limit of this, right? And if that is a number that's not 0, it diverges. Now, this one's a bit tricky. Do you see the 3 over n guy that they've got there? The one at the plus 3 over n guy. Do you see him? Isn't that just a version of the harmonic? And so it diverges. Now, I don't really care what that guy is, right? This bit here. And the reason I don't really care what he is, he happens to be geometric, is it doesn't affect the answer. If you have a series that adds up to infinity, do you think it hurts it or harms it if you add another 2 or take away another 2? Right, because that's all a convergent can do. So if one piece of a pair like this is divergent, the whole thing is divergent. Right. Can you imagine, oh, the first bit adds up to 2, but the other bit adds up to infinity. Well, that just still means the whole thing adds up to infinity, right? You're still diverging. Oh, but the first thing adds up to infinity, and the second thing also adds up to infinity. Well, that doesn't help you any, doesn't it? Still diverge because it adds up to 2 infinities worth, right? It's still broke.
So as long as it inside of the parentheses there, you can find some characteristic of a harmonic, then everything else doesn't really matter.
No, doesn't really matter.
Okay.
Now, can you imagine that this is geometric and that's geometric, and that's too hard to imagine. So let me write one down to show you a different circumstance where it would be important, perhaps, for both pieces. Suppose I had an n equals 1 to infinity, and I had a 3 times a half to the power of n minus 1, plus 4 times 3/4 to the power of n minus 1. So imagine with this ugly guy. Now, if you look at each piece, can you recognize a geometric by its shape? You see, both are geometric. In this question, it would make sense to split it into 2 distinct pieces and find out what's going to happen to each piece. So far, so good. Now, that guy is a half. So R is a half, agreed? And that means convergent. This guy is 3/4, and that also means it convergent. So this guy converges, so does this. Does it not make the whole thing convergent? So far, so good. Now imagine I changed just one value. I made that 13 quarters, right? Well, wouldn't that piece here be 13 quarters, and wouldn't that now be divergent? Right? The common ratio is bigger than 1. That makes this guy divergent. Does it matter that this bit converges if that bit diverges? Because isn't the overall effect that the two of them together diverge? Right. And I normally phrase this by a saying that goes something like this. If one piece is broke, the whole thing's broke. Right. So if one piece is broke, the whole thing is broken. By that I mean divergent. So are we beginning to see some of the little nuances in these, right? That it, you know, you might get a little bit of two different, like the previous one, and then you get a shot at this one and it kind of changes the thing round. Let's throw you into the deep end with this one, which is a version of 13. It's not geometric. I can tell that just by looking at it. That n cubed kind of kills the thing. It's not a harmonic, because that would have to be an n and that would have to be a number. So I'm throwing that one out. So I'm really looking at divergence test here, right? And I want to see whether or not something comes out of it. What is the limit of that fraction as n tends to infinity? Now you can do it either by L'Hopital or you can do it by the relative growth rate. But what is the limit to that fraction?
It looks like either the n is higher, so it'd be
Right.
infinity,
Okay,
faster.
agreed, it is. And isn't that not only, yeah, it's divergence, isn't that heck, yeah, it's divergent? Because if the individual terms become infinite, can you imagine what would happen if you added them all up? Wouldn't the answer be like multi-infinite? It'd be even bigger. So definitely divergent. Now that does not break the test for a divergence test. So let me see if I can find my wording. Does this equal something? Yes, it equals infinity. Is it not zero? Yes, it is not zero, so it diverges. So doesn't this still work? Right? Now, if the limit was 2, it would be divergent. If the limit was 1/10, it would be divergent, right? If it's anything, but not 0, that's the only thing that kills it, right, is 0. If the limit is anything else except 0, you are good to go for divergence. How are we on that? We're good? Well, let's have a look at question 14. And there's something in it that caught my eye. It is going to, well, you have to decide right now what the heck is going on here. But the thing that attracts my attention, looking at my watch here, is do you notice that this starts at 3 instead of the usual 1? Do you see that? Why does it start at 3? Actually, it could have started at 2 as well, but it didn't. Why, let's phrase it a different way. Why isn't n equal 1 the starting value for this?
Because you can't have
So,
0 on the bottom.
right. So can you see that some series have to start at a different number than 1, right? 2 or 3. Are we so far okay? Any more questions on this? Because I'm going to introduce you to a new thing after this. So divergence test, geometric series test, And I'm not even going to call the harmonic a test, but sometimes you can recognize that you're a member of the harmonic family and therefore you diverge. Are we good with those guys? Right. Now we're moving on to, well, 20 minutes, I guess it's going to be an intro to this. We're going to look at what are called telescoping series. And 14 is an example of that. I'm going to pick my own telescoping series. Suppose we have n equals 2 to infinity of 4 over n squared minus 1, right? So far, so good. Now, we're going to employ a technique that is used for telescoping series. Telescoping series are typically, but not completely, fractions. Guys like this. Now, it's helpful to rewrite these fractions by factoring the denominator. Make that n minus 1. Make that n plus 1. It's the same guy, I've just factored that. So if you ever see a fraction where there's a number on the top, or 4n plus 1, something like that, and on the bottom there's two fractions, only two, not more, right, not less, 2 n minus 1, n plus 1 as we have here, then that is an example of a telescoping series. There are other versions, but this is the one we're going to focus on right now. To be able to solve this question, we need to split this fraction into what's called their partial fractions. Now, by sheer coincidence, my Calc 2 students are doing this exact thing today. So somewhere in Calc 2, you learned to do a thing called partial fractions. I'll show you what it looks like. Partial fractions is when you take a fraction like this and you break it into two pieces. And the first piece is going to be a, where a is a number that we'll find out eventually what it is, plus b, which is the other one. Do you recollect seeing this process of taking a single fraction and breaking into two pieces called partial fractions? You're nodding, John, like you remember it. You remember seeing it somewhere?
Yep.
Right.
I
A while
seen it.
ago.
I see.
What? A while ago.
Yeah, and 152, right?
Yeah, 152. So there are two methods that you can use to find these missing numbers, the a and the b. So once I know that's 3, I'll know what that is as well, right? And there's a kind of pattern that goes with these. We'll talk about that later. But I need to have a way of breaking this into its two constituent pieces, right? And that means I need to find a and I need to find b. The first method, I'll put that in a piece of paper. The first method is called the cover-up method. Any of you heard of that term, cover-up method? No. It's a really cool trick. It's pure magic, but if you can perfect it, it makes these questions very quick. If you cannot, if it just doesn't make sense to you, you can't figure it out, there is a second method, which is one everybody uses. It's called the general algebraic method. So I'm going to show you how to get this answer the value of A and the value of B using the cover-up method. Now, this is a very visual trick, right? And it is basically magic, like it's a trick. And you've got to, I've tried to write it down in English and it just doesn't make sense. You got to see it. It's one of those, you just got to see it, right? So let's start by finding A, right? So I want to know what number this is, and it's going to be a number, right? There's an n minus 1 in the bottom, right? So you go over here and you cover up the n minus 1, right? So do you see the left-hand side is now really a fraction? If I pull that 4 along. 4 on the top, n plus 1 in the bottom, agreed? Now, to get A, you take this fraction here, right? The 4 over n plus 1, and you replace the n by whatever number makes this guy 0. Well, the value of n that makes n minus 1 0 is 1. So you plug in 1 here, and you get 4 over 2, and 4 over 2 gets you 2. And that's the cover-up method finished. Okay, let's show it again. I want to get that guy, right? The B. Cover up the n plus 1, right? That guy there. What value of n do I use the second time? Well, whatever makes that 0. And the number that makes that 0 is -1. Great. -1. 4 over -1 take away 1. 4 over -2 is -2. There are your partial fractions. Do you recollect ever seeing that technique before?
I've never been shown that.
But it's kind of nice, right? It's kind of magic, but it works. And one of the advantages is that it's really fast. If you know how to do it, you can do the answer in less than a minute, right? Now, here's a second thing that's only true about these questions, the telescoping series ones. These two numbers will always be the same number, and one of them will be plus and the other will be subtract. So it's going to be 10 take away 10, 5 take away 5, a half take away a half, right? So if you don't get both numbers the same, you're screwed up somewhere, right? That's kind of guaranteed for this situation.
So in the cover-up method, then you're covering up n plus 1 that last time.
Yeah.
But you're actually finding out what makes n plus 1 go to 0, right?
Yep, and reusing that value of n on what's left. So n plus 1 equals 0 when n is -1. I'm plugging in n equals -1 to what's left. By that I mean this bit. And the answer you get is -2. Okay, now, but
Got it.
remind me tomorrow to show you the general algebraic method, because we don't have enough time to finish this off and go back to that. So right now, all I have got is n equals 2 to infinity, and I've got my fraction split into these two guys, right? Now, if you plug in 2, you'll get 2 over 1, take away 2/3. If you plug in the next number 3, you get 2 over 2, take away 2/4. If you do the next one, you get 2 over 3, take away 2/5. If you do the next one, you get 2 over 4, take away 2/6. And then if you keep on going, won't you eventually get, well, let's put it here, you eventually get 2 over n minus 1 over 2 over n plus 1. Can you imagine just generically stopping at some place n? Now, one more piece of the puzzle. If that is the last term, right, that's what you get when you plug in n. Essentially, I'm getting what's called the partial sum. What would the term before it look like? And that's a little bit trickier, right? Well, you know, if this is 2, 6, this guy here is 2/5. This fella here is -2 over n plus 1. What would the guy here be? The one just before that term? Well, notice what happens here. 5 gets you 4, gets you 3, right? Are you comfortable with that guy? Gets you this guy. And what would this guy get you? N minus 1. What would go here? N plus 1 became an N. N minus 1, what would that become? What do you do to this to get that?
Hmm,
N minus 1 becomes
N minus 2.
N minus 2.
So basically, you just figured out how you got from 5 to 3, or 6 to 4,
Yeah.
or 4 to 2.
Just did the same thing with an N, or an N plus 1, or an N minus 2, whatever I'm starting with. Now, if you look at this and imagine this is like an infinite number of terms, right? Or at least an uncountable number. Something interesting happens to quite a lot of them. Do you notice that this negative 2/3 eventually gets killed off by a positive 2/3? And do you know that this negative 2/4 gets eventually killed off by that 2/4? I'd have to do more terms, but can you trust me that that negative 2/5 gets killed off by somebody over here, and that negative 2/6 would get killed off by somebody over here? In fact, there are only 2 terms that don't get killed. That one and that one. All the other terms will get killed off. Now, we'll talk about the end in a minute, but right now, there's a 2 left over, 2 over 1, and there's a 2 over 2 left over. Now, it's a bit trickier, but here it goes. Do you see how these 2 are the first term in each? What's going to happen then is that the last 2 in each will also survive. So see that one there and that one there, he'd be killed off by guys over here. So telescoping, can you imagine a telescope where a big long thing gets pushed down the old pirate telescope to a thing that size, right? Big, small. Big, small. So the 2 terms that are left over with are these 2 guys. Now, if you then say, well, this whole thing really simplifies down to that, what's going to happen when n goes to infinity? Well, that's still 2, and that's still 1, but won't those 2 things basically disappear? And so what you have is that the limit is 3. So in this telescoping series, by this process of breaking it into this guy here, breaking it into its partial fractions, and then writing down the first 5, 6, 7 terms so you can see which numbers survive, and then make an intelligent guess about what is left alive at the end. These 2 stay put because these are numbers, but won't the bits that are left at the end dissipate to 0? You know, as
Oh,
n
so-
is 1,000,000.
So how do you know that 2 over n minus 2 and 2 over n plus 1 disappear? How do you know that?
These 2 are, I'll call that first place, right? The guy in the left, first place. The guy in the left, first place. So to balance it, the guy on the end survives. Does that make sense? If the guy at the front lives, then to compensate for that, a guy at the end will live, right? Front and end, front and end. That's kind of the argument. So,
Okay.
just for argument's sake, can you pretend for a minute that this guy survived and this guy survived? Let's make it even easier. Let's suppose only one of them survived, right? This guy here. That's the only one that survived, right? Everything else get killed off by something else, right? That could happen. So I've got one term left here. Only one of these two terms would survive, right? It's a balancing act, right? Everything else gets killed off by somebody. This guy is in position 2, then won't this guy here be the survivor? So that guy lives, this guy lives, right? Second guy lives at the beginning, first guy lives at the end. First guy lives at the beginning, last guy lives at the end, right? It's the opposite, right? Like a left and a right. You see what I'm getting at?
Yeah.
That gets you a finish. These guys are easy because even if you sort of got them half right, no matter which ones you pick, won't they still disappear to 0 and you'll still get the total right? So it's still, we want you to do it correctly, but it's not going to affect your answer if you accidentally picked the wrong one. Okay, everyone should have got the report. So that's week 6 report out. So you want to go looking for it. It's in the usual place. I'm going to be leaving in a few minutes, but I thought I'd best wait, for any last minute questions that you might have. Otherwise, bye-bye for now.